Oh yes, yes, here it is. The ubiquitous correlation and how it does not equal causation. Anyway, we're going to skip over that whole thing of no causation stuff for now, because I think it's been beat into everybody's heads over and over and over and over and over again if you've spent any sort of time in a psychology class ever. Any time in your life. Anyway, let's just go on because we want to look a little bit at this, a little bit about how it's all done, and some alternatives to the standard correlation procedures that we typically use. So, all right, correlation is essentially just based on the concept of covariance, right? Covariance is, in a nutshell, the most pure form of correlation. It's the most simple. It's when two things change together. Do they co-vary? Right? So covariance is the most simple form, it's the most pure. So ultimately we're always asking the question, how much does one score covary, or how much does one score vary with another one? So as I go up in temperature, will ice cream sales go up? Well, yes, of course they will. And how about ice cream sales in crime? Of course they will. Why? Because they're related to temperature. Anyway, so you get the idea that as one goes up, the other one's going to go up. The problem with covariance by itself is that it's not standardized, right? So you can't really compare ice cream sales to crime and all that stuff because they're on different scales of measurement. It's like an apples and orange type thing, and again, so there's the scales of measurement comment. So covariance in miles. So if we're looking at the example here is miles and kilometers. It doesn't convert directly. So, for example, if ice cream sales are done in dollars and you're wanting to compare that to, say, crime rates, which in one sense, I guess you could do it in dollars, but in another sense you wouldn't. You'd say how many times did this happen or what types of crimes happen and those types of things. So you couldn't really compare those directly because there are two completely different scales. So the numbers won't match up. So we have to standardize stuff, right? So that's that whole thing that we talked about earlier with going back into doing the z-scores and all those things. So ultimately, when we get into a correlation, what we're going to do is work with those. Wind blew my door open. We're going to work with a standardized version so we can compare apples to oranges and we can compare miles to kilometers and those types of things. So let's look at the most basic correlation that we typically use, the one that probably most of us are familiar with and have seen a million times, and it's called the Pearson Product-Moment correlation. You can thank Pearson for that. He's kind of a creepy looking guy, but you can look him up on the internet and see Pearson. Just type him into Google Images and you'll see why anyway, he's a funny looking guy, but he did a lot of cool stuff in statistics though. So all right, so his job it's not like he woke up one day and was assigned to do this. No, he decided to do it. He figured out a way to standardize covariance, right? Which is really straightforward. Look at all that highly complex, beautiful formula, right? Sure, okay. So really straightforward. R is the correlation. That is the value, right? R is bound by 1 and -1. We'll look at that in a minute. So the XY that's next to the R there, that's just saying that variable X and variable Y. That's all it's saying. Ice cream sales and crime, heat and crime, whatever you want to look at. All right. So that's all it is. So we're going to sum the Z-scores times the Z-scores and divide that by N. Okay. That's all we're going to do. It's really straightforward. So a z-score for each one, z-scores of x, z-scores of y. You're going to get a bunch of them, right? So let's say you've got 100 data points in each. So you got 100 of these things that you're going to have to do, and then sum them all together and divide that by your sample size, which in this case would be 100. And then so there's the product, right? So the Pearson Product-Moment. Pearson's just the guy's name, Product-Moment. We can look at again, the product is you're multiplying each one of those variables together, the z-scores, so you're multiplying those two z-scores, so there's your product, and then the moment, just indicating that you're dividing that out to look at an average, in a sense. So we're going to multiply things together and sum them all up, and then get an average of that by dividing it by n, and so we get in a sense, an average relationship between these two products. Okay, so sum of the standardized distances from the mean multiplied by each other. All right. So we're going to multiply each one of those individual data points and sum them up and divide it by n. Right? So we're calculating really a standardized covariance score, because if we were to calculate covariance, you would just do it without the standardization. So it's really straightforward, and it's bound by -1 and 1. So there is no a lot of people think that -1 correlation is weak or bad correlation. No, it's actually -1 is unbelievably powerful. It's just as strong as a 1. It just goes in a different direction. So with a -1, then you have one score going up and the other one's going down. With a +1, both scores are going up. Very rarely are you ever going to get a correlation where a perfect correlation like this, a -1 or a 1. Usually it falls somewhere in the middle. 0 is like no correlation, so there's just no relationship between the data at all. So let's go ahead and look at some of these things here. I've got some examples. So let's look at positive correlation. Notice that as the first column there, so we got two columns for positive correlation. So we got 2, 5, 7, 3, 5, 2, 10, 14, 6, 10. As each one goes, as the left column goes up, the right column goes up. No correlation. We have, and don't worry about the sum so much. That was me just kind of playing around with stuff. The no correlation, we've got the 3, 6, 2, 7, 1, and then notice the other direction that sometimes it drops. So if you're looking at just the first two data points, it looks like a negative correlation. But then you add that third data point in there, it's like, oh, well, it's kind of a positive, and the back to the other one's kind of an, oh, now it's just all confusing and we don't have no correlation. So the other one, as one goes up, the other one goes down. 4 is a -2, and it goes up on the left column, goes down on the right column, goes down on the left column, goes up on the right column. So it's always going the opposite direction, right? So that's the negative correlation. So that's essentially how this looks. You can kind of see it in your data, but when you get hundreds and hundreds of data points, you're never going to see it. You have to run the numbers to find out. Right? So what do we do with it after we get it? So we're gonna calculate the z-score. We're going to calculate the Pearson Product-Moment, the R, and then we get to run some significance testing. Why do we do, or how can we do that? It's because these are already in z-scores. That we already know the probability of obtaining these results. So ultimately, the R is not actually normally distributed, so there's a small adjustment that's done for that. It's a little bit beyond the scope of this course, but just know that we can convert that to a normal distribution, R. So remember, when we talk about the statistic distribution, we're saying that all the possible R's that you can get, and how are those normally how are they distributed? Well, because it's bound by -1 and 1, there's no way for it to possibly be normal. But we can tweak it a little bit and make it close, which then gives us the ability to look up the probability of obtaining particular scores. Ultimately, all we're doing is asking this question: is the correlation different from 0? If it is, it's significant. That's all there is to it. So we're just going to calculate the z-score of the R, all right, and divide by its standard error, and then we're going to say, is it significant or not? And typically speaking, and this is for the p.05 level, we're saying that if that z-score for the correlation, not each individual data point, but for the correlation as a whole, exceeds -196 or +196, we're going to say it's significant. But of course that assumes that it's at a 0.05 level. What was I going to say? Shoot. I hate it when my brain just shuts off like that, especially when I'm talking about correlations. Calculate z-score, R, divided by standard errors. I must have covered it. There was something I was going to say in there. It might have even been funny, but it's not going to be funny now. All right, some assumptions associated with this. We have to have interval level data for basic interpretation. If you don't have interval level data, then it's not going to make much sense. You're too much binding going on in your data. And then if we're looking for significance, then it has to be normally distributed. Now there's some argument here about how, if it actually has to be normally distributed or not. My opinion, it was settled in the 1970s with a pretty clear article, and I'm forgetting the author's name as I sit here to talk about this, but it basically says you can't draw any conclusions if it's not normally distributed. Done. And this article covers hundreds and hundreds and hundreds of different sample types and conclusions that you can draw from that, and assumptions based on normalcy and not based on normalcy and things. So I find it very important to make sure that your data is normally distributed if you're going to use this. Some people argue, well, if you have a large enough sample size, then it's okay. And again, I'm not sold. For me, the data that I've read doesn't indicate that that's actually accurate. That if you're not normally distributed, it's not going to work. Okay. That was what I was going to talk about earlier, was that significance in correlation testing, it tends to relate heavily to sample size. So if you have a large sample, it's going to be easy to get significance, and we've talked about that previously, and ultimately what happens with that is that it becomes very sensitive to significance, very sensitive to that random, the non-random stuff. So you can have a very small correlation, let's say a 0.1, with a huge sample size, and it'll be significant. But that's not very impressive, right? The meaningfulness there, the effect size is non-existent, so we have to worry about that. All right, what can we do with correlation? Well, right off the bat, all you can say is variable x is related to variable y, but we can square the correlation. Okay. And if we square that correlation, right, we have what's called variance accounted for. So VAF, if you will. So R squared is always the amount of change in one accounted for by the other. So as temperature goes up, how many do wildfires go up? If wildfires go up, do temperature go up? Okay, so you can always read a correlation in any direction you want. So let's look at it. Look at this as an example. Let's say we've run this correlation in temperature and numbers of wildfires, and let's assume, again, I'm making up data, that it's a 0.9. It's a really strong correlation. Watch what happens when you square it. You get 0.81. Well, that's 81%. So R squared is basically just saying that 81% of the variance is accounted for of one of those variables by the other. So the number of wildfires, 81% of that, according to our data, is accounted for by the temperature. Of course, you got the other side of that coin, which really doesn't make any sense, that the temperature is accounted for by wildfires, but that's the beauty of a correlation. It does read both directions, and that's why we say it doesn't equal causation, right? Because you can interpret it in any direction you want. Here's the interesting thing. This is darn near a perfect correlation. You get this correlation in psychology, you're going to be excited. You're going to be getting published, and you're going to be, wow, I found something really cool. But don't forget, you just left 19% unaccounted for. 19%, let's assume that we've got a correlation of 0.9, the temperature here accounts for 81% of wildfires. That leaves 19% left unaccounted for. So it's huge. So even with a darn near perfect correlation, a 0.9, you still have 20% of the explaining left to do, essentially. So what's that other 20% that contributes to wildfires? Of course, it's really easy when you think about wildfires. Well, it's human activity. You know, there's somebody playing around with a lighter or something like that. Or lightning or something. Sure, okay. But when we start to think about this in terms of psychological stuff, we often get correlations that are around the 0.5 range, and we say, ooh, they're significant, look at that. Okay, 0.5 times 0.5 is 0.25, right? 25, you've only accounted for 25% of the variance of one of those variables. Think about, let's make another one up here. So correlation of 0.5, let's say it's significant because we've got a lot of people, and we're going to relate video game playing to violence in schools. Oftentimes you're going to run into stats like that. It's going to say it's significant. Wow, the authors are going to really be building it up. Look, we have significant correlation between these two variables. Always square the R value, because that'll tell you how important it really is, right? So if we have that video game and violence in schools, all right, 25% of violence in schools, if that's our statistic, and again I just made it up, would be accounted for by video game playing or violent video game playing. Okay, that leaves 75% unaccounted for. Great, it may be a significant thing, but it's not that meaningful, right? So we got to always watch out for that. All right, if we don't have normally distributed data, we're not in a dramatic amount of trouble. We can use Spearman's row or we can use Kendall's tau. So Spearman's row, it's made for non-parametric stuff. It's going to use rank scores, so we're going to rank everything. All right. So we're going to rank all the scores from variable 1, rank all the scores from variable 2. You mix those all together at the same time and rank them all. Okay, that's the idea. So you mix it. You take your two sets of numbers and then rank everything. And then you split them back out into their groups, and then you multiply everything together. Basically, it's just a Pearson's correlation with using ranks instead of raw numbers. And when you rank stuff, it tends to get a closer approximation of normal distributions for whatever reason. So that's just what it does. So then you can use the basic procedure that we talked about earlier, and you get the same result. Interpreting the R squared here is a little bit odd. It doesn't make a lot of sense to say that's the variance accounted for because you're looking at ranks, so we tend not to do that. So Kendall's tau is another one. It's non-parametric once again, used in place of Spearman. This one better estimates the population, and we use it when you have a small data set or you have many tied ranks. So keep in mind, if you're reading in the articles, in journal articles, and you see a Spearman correlation or Kendall's tau correlation, then know that the author is doing their best to accurately represent their data and they're not trying to pull the wool over your eyes. You won't see these very often. You should see them more often than you do. If an author does not report on whether or not their data is normally distributed, then you don't know if the Pearson is the appropriate statistic. So if they have reported on whether or not it's normally distributed, then you'll see them using the appropriate stat, either Kendall's tau, which is the more common one to use here, or Spearman's rho, and or the Pearson, depending on the type of data you have. So that's essentially it for correlation. We don't need to go into how to calculate Spearman's and Kendall's. It's really straightforward. So and it's beyond, again, we're not talking about generating stats here. We're just talking about understanding how to use them, or how to interpret them. So that's that, and enough for correlation. And I'll come back and talk to you about some other stuff down the road. Take care.